Hello everyone and welcome to the second part about the curse of dimensionality. In this part, we will explore rather an intuitive solution to the problem of dimensionality. Yep, you guessed it right. Why don't we add more observations? Let's revisit the simulation we did to illustrate how distances inflate with the increase of dimensionality. Now we will add a constraint on our distances, such as for all of our observations, there is at least one observation whose distance is equal to 1 from all points. In other words, we will control the distance increase for all of our observations, and we will look for the number of observations that will enable us to do so. So here's the math of that. Don't worry, I promise I will explain this as clearly as possible. The constraint we have talked about is put mathematically as follows. For all our observations, there exists at least one other observation whose distance from all the observations cannot exceed 1. The distance is nothing but the Euclidean norm of the difference xi minus x, which means that x is inside the unit ball of center xi. So what the hell is a unit ball? I will illustrate it in a two-dimensional space, because that always makes things simple to understand. Suppose our observation is the point with coordinates 1 and 2. The unit ball of that has this point as a center and 1 as a ray, so it's nothing but this disk. See how easy that is? And if we are in a three-dimensional space, that unit ball will be the sphere that has ray 1, and so on. Now let's go back to the math. Since every point generated is inside the unit ball, that means that all the points inside the Cartesian product of our interval is inside the intersection of the balls. That means that the volume of our pool used to generate the data is smaller than the volume of the intersection of unit balls. The former is equal to 1 since the intervals all have length 1, and the second is n multiplied by the volume of the unit ball. We added the parameter p to the ball to pinpoint the dimensionality of the ball. So here's what we need. In order to control the distance inflation, we must ensure that the volume or the number of our observations is greater than 1 divided by the volume of the unit ball, which is equal to this messy formula. We will not get into the details of how that is derived. Now it's time to do some coding. We will explore how the volume of the unit ball changes in function of the dimensionality, and I promise you, you are going to be shocked and amazed. The first line is an empty vector that I will use to store the different volumes calculated. The second is a loop where we calculate the volume of this ball for dimensions ranging from 1 to 100. And the third is the plot in order to see the evolution of the volume. So let's execute this code together. Here is the plot of the evolution of the volume of the unit ball. It starts to increase until it reaches this point. We're talking about 10 variables, and then when we reach 20 variables, look at this. The volume of the unit ball becomes literally 0. So if you try to make sense out of that, good luck. I mean, look, I will show you the last values, like the last 10 values of the volume. They're literally zeros here. Look at this. It's 5.57 multiplied by 10 to the power of minus 32. So the volume, not only the distance is distorted, but the volume becomes literally insignificant. Now, if we have 20 variables, we will need 39 observations to keep the distances from inflating. And if we have 30, we will need 45,630 variables. For 50, we need 5.7 multiplied by 10 to the power of 12, and the rest is just insane. So this proves that we cannot overcome the curse of dimensionality just by adding more observations. Not to mention that even if we could, the cost would be heavier than most organizations can handle. For more on high-dimensional statistics, I will leave a link to an amazing book written by Christophe Giraud, as well as a link to his YouTube channel. Most of the material to create the first part of this series is inspired by him.